This chart is a useful one to refer to as we start to talk about the NMR spectra of different compounds, and it points out that the hydrogen's environment really does have an effect on its chemical shift and provides a means for helping us to confirm the structures that we suspect we may have for a particular compound, or in some cases allows us to come up with a structure if all we know are just the numbers of each type of atom. And we'll be doing some of that as we go along. If you look, for example, over here at the alkyne they've got pictured, what this is saying is that if you have a hydrogen attached to a carbon-carbon triple bond, then that hydrogen will show a resonance somewhere between 1.8 and 3.1. The exact value will depend on what's going on the other side of this triple bond, because it will depend on the rest of the molecular structure. But that tells us that if we suspect we have an alkyne, that this will kind of confirm that if we do get a resonance in that region. Now, notice there's a lot of overlap between that region of chemical shifts and a lot of the other ones around here. For example, if you have a chemical shift between 2 and 2.5, while that might correspond to the hydrogen on this alkyne, this chemical shift is also very much associated with a hydrogen attached to a carbon that's adjacent to a carbonyl. That happens a lot in things like ketones and aldehydes and carboxylic acids and so forth. So oftentimes when a chemical shift is in that range, that's what it's indicating, especially if we've got other reasons to believe that there is a carbonyl in that molecule. The lowest chemical shifts are down here in things that are alkanes, where we just have methyl groups, CH2s, and no other atoms except carbon and hydrogen. They give chemical shifts of around 0.9 up to around 1.5 or so. Close to our standard TMS, which of course gives that signal at exactly 0 on the chemical shift scale. And that's because the methyl groups in TMS, just like methyl groups in regular alkanes, they are said to be heavily shielded from that magnetic field, and so that correlates to them having low chemical shifts. If you start replacing those hydrogens with some other atoms like halogens or oxygens, you turn your alkanes into alcohols, ethers, things like that, it turns out that the chemical shifts go up because those hydrogens are de-shielded. They are more readily exposed to that magnetic field. Notice you can't really tell the difference between, say, a chloride and a bromide. They both have very similar ranges, but you could certainly tell an alkyl halide in general from just a plain old alkane. And in real life, those things all tend to be colorless liquids, so that's one way to quickly establish whether you have an alkane or whether there's a halogen there. But you would need other information to tell you the difference between it being a chloride versus a bromide, for example. Another great usefulness of this chart, way over here, aldehydes and carboxylic acids. Notice they give chemical shifts that don't overlap with other types of compounds. If you have a chemical shift between 9 and 10, that's practically always because it's the hydrogen that's on a carbonyl and an aldehyde. And so it can tell you you do have that kind of compound. The hydrogen on the carboxyl group and a carboxylic acid, notice here we get really high chemical shifts, around 10 to 13. And practically no other compounds give chemical shifts in that range. But a lot of overlap is certainly seen here, so while this is a helpful table, you normally have to have a little bit more information when you are trying to distinguish among these possibilities that are all kind of on top of each other. One final thing here, this AR does not stand for argon. It stands for the word aryl, and aryl in turn refers to compounds related to benzene. Benzene is what you would get if this were a 6th hydrogen, and so these hydrogens that are attached to this 6-membered ring with the alternating double bonds, that's called a benzene ring. We'll see a lot more of that in the next unit when we talk about the chemistry of such compounds. But for now, just realize that AR does stand for aryl, and it refers to the chemical shift of those particular hydrogens, around 6.5 to 8.5, and that shows up a lot in NMR spectra, so that's a good range to keep in mind.